Welcome again. Can you hear me?
Yes, sir.
Okay. Oh, so I was telling you about the reference electrode. This is dipped in the same solution as a test solution, and therefore the two half cells are now together in the same solution, and they are connected with respect to each other, and therefore they form the complete electrical circuit. Okay. Now, this particular reference electrode, it has a small leakage of ion. There is a particular thing which is called as a salt bridge. And through the salt bridge, the ions from the reference electrode can actually go into the solution. And therefore, there is a continuity of current between the reference electrode and the sample electrode. Of course, one thing you should remember is that the actual electric flow is not there. Okay. So this particular device is only measuring the potential difference, okay, without any flow of electric current. This is a very, very important statement. Okay, now from these figures, I think you can understand the construction of the glass electrode as well as the reference electrode. What we have in the glass electrode is a metal wire. It is usually made up of silver. Okay, so silver metal wire which is dipped in AgCl. Okay, AgCl is a coating. There is a coating of AgCl, and that coating actually prevents the dissolution of the metal wire in the solution. Okay, and this particular Ag wire coated with AgCl is actually placed in a saturated KCl solution here. Okay, and then I think you can see this. The distal part of the tube is actually coated with the thin glass membrane. This glass membrane or glass bulb, as it is called, this is the part which is sensitive to the protons. Okay, very important. And then you have the reference electrode. In the reference electrode also we have a metal wire. That metal wire could be again made up of Ag, okay, silver, and then it is dipped either in AgCl and that is itself is dipped in KCl, or sometimes it is also in mercury chloride solution. Okay, so that is a difference. And then there is a thin a pin here. Can you see the porous plug here or porous pin? And this is the region through which this particular electrode is in contact with the solution. So ions can actually freely pass through this particular region, this pore, actually, okay. And because of that, the electrical circuit between these two different electrodes is complete. Okay, that is to say the two electrodes are actually physically in contact with each other, and chemically also they are in contact with each other. Just to give you another view of the two types of electrodes, this is the glass electrode. Okay, and there is a silver element or silver metal wire which is dipped in silver chloride. Okay, and this is put in KCl solution, right? And then this is the reference electrode. Reference electrode, the most important point about the reference electrode is that the potential of this electrode is known and it is a fixed potential. Okay, and therefore it is called as the reference electrode. Reference means what? It is a known electrode with a known electric potential. Okay, and this particular electrode has an unknown potential because that potential will actually depend upon the solution in which we are keeping that electrode. Okay, the test solution, and depending upon the proton concentration of the test solution, the potential on this particular electrode will vary. Okay, and what we actually do is we find out the difference between the electrode potential. Okay, difference between the potential of the two electrodes, and that difference is proportional to the proton concentration of the sample solution. Okay, so more the proton concentration, more will be the difference in the electric potential. Okay, and less the proton concentration, less will be the different, less will be the potential difference. Okay, then these are some more details about the glass electrode. This glass envelope is with buffer of is actually having a buffer, and that buffer has a known ionic strength. For example, it has say 0.1 molar of HCl within the glass bulb. Okay, and in this glass bulb, within that particular solution of HCl, or KCl also, an Ag wire or silver wire which is coated with AgCl is immersed. Okay, and this particular electrode will generate a certain potential, and the sensing element actually is composed of the glass membrane tip, and this is sensitive to hydrogen ions or protons. Okay, it is a 0.1 millimeter thick, or rather a thin glass tube, glass membrane, and this is made up of a special type of glass which contains silicon dioxide, and this silicon dioxide is actually doped with alkali metals and alkaline earth metals, for example lithium, beryllium, sodium, and so on. Okay, now the pH measurement is actually based upon the chemical reaction which happens between the sample solution and the membrane surface. Okay, so sample solution contains the protons, and these protons are actually going to stick on the outer wall of that glass bulb. Okay, and because of that, a particular potential is created. In fact, it is something like this, that if a large number of protons are there on the outside wall, and there are also some protons from the inside wall also, okay, outside and inside. Now, if the proton concentration outside is very high, that is, if the pH, if the solution is very acidic, okay, then a kind of pressure is built up. Okay, the protons will exert a pressure on that glass membrane. That pressure is nothing but the electric potential. Okay. The electrode which is in contact with the aqueous sample causes hydration of the glass membrane. Okay, so these silica groups, that is SiO groups on the glass, these get hydrated because of the water, and because of that the silica SiO is converted into SiOH plus. Okay, so that is called hydration of the membrane. Now this hydration is taking place both inside and outside of the glass membrane. Now, one thing which I should again tell you is very important, and that is this hydration of the membrane is very important. If the membrane goes dry, for example, then it will not be sensitive to the protons. Okay, and therefore maybe I don't know whether you have actually used the pH meter in the college, but if you had actually used the pH meter, then maybe your teachers might have told you in the laboratory that the glass electrode must always be kept immersed in distilled water. Okay, because if it is not kept in distilled water, then the hydration property will be lost, the membrane will become dry, and if the membrane becomes dry, then the pH electrode is of probably no use. Okay, now this is how the half cell would actually look like. AgCl, okay, that is the metal wire which is dipped in HCl solution or KCl. Okay, and that this particular glass is then coated with the glass membrane. Okay, and then this glass membrane itself is in the test solution, the probe solution, and then within this solution we have the reference electrode also. That is how the complete electrochemical cell or the galvanic cell is formed, and the potential difference which I am talking about is actually developing here between the glass membrane and the test solution. Okay, so that is where the potential difference is generated. Okay, and then in this particular test solution we have the reference electrode. The reference electrode also has silver metal which is dipped in AgCl, which is itself in a buffer containing KCl. And then there is a ceramic junction or the pore which I was telling you about. Okay, and from this pore the ions can freely move, and therefore this electrode, reference electrode, and the sample electrode, they are both in contact with each other. Then one important thing which you should know is, I'm not going to read the entire slide, but I'll just tell you something very important, and that is the protons which are present outside the glass membrane and the protons which are present inside on the inside surface of the glass membrane. The protons cannot actually travel through the membrane. They cannot travel through the membrane. Okay, but there are sodium ions. The sodium ions which are present within the membrane, they can be exchanged for the protons on the outside or on the inside. Okay, And what happens is only a potential difference is created on both sides of the glass membrane, right? I go to the next slide. Okay, this sentence is also very important. If there is a gradient of proton ion activity, I'm using this term activity. Okay, so all these protons are active protons, right? These are able to generate a gradient or potential difference across the membrane. Okay, so if there is a gradient of protons, or if there is a change in the pH of the test solution, then it will generate a potential. And this potential which is generated is given by an equation, and that equation is called as the Nernst equation. Okay, we are going to see what is the Nernst equation, although it may appear to be a little complicated for you, but it is actually a very, very simple thing, provided you understand the concept of that particular equation. Okay. Well, so this is the Nernst equation that I was telling you about. This particular equation tells you about the measured voltage. Okay, that is the, what is the measured voltage? It means the voltage difference between the two types of electrodes. Okay, so what is that voltage difference? It is given by capital E is equal to E0. E0 is the standard potential, standard electrode potential, okay, or the potential of the reference electrode, plus 2.303 RT upon NF log of the proton concentration. Again, that proton concentration is given in square bracket. So whenever something is written in the square bracket, it indicates the active concentration, not just the concentration, but the active concentration. So when I say active concentration, it means the actual protons which are there in the liquid, not in the form of water molecule, or not in the form of the any other chemical species, but the free ions of hydrogen, that is the protons, which are available. Okay, and why they are available? They are available to generate the electrode potential. Okay, so this particular equation is now relating us to what? First is the electrode potential, the potential which is generated, okay, in the electrode, and that is equal to the standard electrode cell potential, that is the of the known reference electrode, plus R is the universal gas constant. Do you know this particular term, R? I think in your physics somewhere you have learned about the gas constant. T is the absolute temperature. Okay. Now, why these two things are there, gas constant and the temperature? That is to tell you that these particular ions which are there in the solution, ions, that is the protons which are present in the solution, these are now behaving like gas atoms. Okay, gas atoms. How are gas atoms? Gas atoms are free to move about anywhere, isn't it? Free flow of gas molecules or atoms. Okay, so we are imagining, we are assuming that whatever is happening in the liquid is actually similar to what is happening in the gaseous state. Okay, we have to consider this assumption because that assumption will only help us to write the equation or to understand how the electrode potential is generated. Okay, and then we are adding this term for temperature. Again, the reason is that with increase in temperature, the mobility of the ions will be more, and with decrease in the temperature, the mobility of ions will be less. Okay, and therefore, if you want to know anything about the mobility of the ions in the solution, we should also talk about the temperature. We should know what is the temperature. Is it right? Then N here, small n, is the valency of the ion. Now the ion that we are going to talk about is the proton. And you know that proton carries a single unit positive charge. Okay, 1 unit positive charge. And therefore N here is actually +1 always, because you are talking about protons. Okay, F is the Faraday's constant. Okay, what is Faraday's constant? Will you be able to tell me why we are putting this term Faraday's constant here? Or maybe you will find out the answer later and tell me in the next lecture. Okay. Although the next lecture will be pertaining to spectroscopic techniques, but doesn't matter. Somebody can just tell me what you have understood, why this Faraday's constant is included in this particular equation. Okay. And then we have log of the proton concentration, active protons, log of active protons. Okay. So if I tell you that I have already said that this is a very simple equation, simple because I just want to tell you that all these terms here, see the electrode potential of the standard electrode is a known thing. Okay, it is a constant. 2.303 is a constant term. It is not going to change. Okay. Universal gas constant also is a constant. So it is not going to change. The temperature, for example, if we consider the standard temperature, what is the standard temperature? Usually used for any sort of your physical equations.
37.
37, is it standard temperature? Standard temperature, standard pressure, standard pH, all these terms are usually considered in order to understand a particular system, isn't it? The standard temperature is 25 degrees. Okay, remembered? Okay, so this temperature also is a constant. N is the charge on the ion proton plus 1, that is a constant. F is a constant, Faraday's constant. And therefore, if you look at this equation in a way, this complete term here, E0 plus 2.303 RT upon NF is itself a constant. It is a constant. Okay. And this particular constant is also called as the Nernst constant, or it is also called as the Nernst factor. Okay. So everything else here, a constant. And now what is variable here is only this particular part. Log of the proton concentration is a variable part. Why it is variable? Because this concentration of the protons will depend upon the sample solution. If the sample solution is very acidic, the proton concentration will be high. Okay. If the solution is less acidic, then the proton concentration will be less, or the hydroxyl ion concentration will be more. Okay. And therefore, you will appreciate the fact that this particular E value, that is the potential which is generated on the glass electrode, is directly proportional to the log of the proton concentration. Okay. E is directly proportional to log of H plus. That is the basic principle of the pH meter. Have you all understood?
Yes, sir.
Okay.
Yes, sir.
म्हणजे हे सगळं तुम्हाला सांगण्यासाठी मी जर हे केलं तर त्याच्यात बेसिक एकच गोष्ट आपल्याला कळायला पाहिजे की द पोटेन्शियल विच इज डिव्हेलप्ड अक्रॉस द ग्लास इलेक्ट्रोड, ओके, ग्लास मेम्ब्रेन is directly proportional to log of the proton concentration. Okay, and that is why we are able to measure the pH, okay, using the pH meter. So what we are using is we are using a voltmeter or a potentiometer, okay, and this voltmeter is giving you the measure of the proton concentration, because the membrane which is used on the glass electrode, that is sensitive to the protons. More the number of protons, more will be the potential which is generated. Less the number of protons, less will be the potential which is generated. Okay, and the potential is not directly determined, but the difference in the potential between the glass electrode and the reference electrode, that difference is measured, and that difference in fact is proportional to the proton concentration. Is it right? Okay, then coming to the reference electrode, the reference electrode forms another half cell of the galvanic cell, okay, or pH electrochemical cell, and the circuit can be completed only when the measuring electrode is combined with the reference electrode. Okay, so this particular word combined actually means two things. Either the two electrodes are separate, they are separately placed in the sample solution, or sometimes that becomes a little cumbersome, little difficult to manage, because if your sample container is very small, then holding the two electrodes together in that container will be a little difficult job. And therefore, nowadays what happens is we have an electrode which is a combination of the two electrodes. Okay, and that particular electrode is called as a combination electrode. Okay, so combination electrode actually has two electrodes in one electrode, two in one. Okay, the test electrode or sample electrode plus the reference electrode together, they make what is called as the combination electrode. Okay, so this particular reference electrode contains a reference element that is a metal wire, usually made up of silver, and this is placed, or this is immersed in an electrolyte solution, right? And at the tip of this electrode, there is a salt bridge. Okay, this particular salt bridge is, or instead of a salt bridge, there could be a ceramic frit, okay, ceramic plug, as you can call it, or a Teflon plug, or an asbestos plug. The only idea of using this is to make that particular solution inside, okay, continuous with the outside solution, so that ions can pass through. And when the ions can pass through it, then it means that the electric circuit is made complete. Okay. So this is what I was telling. The potential of the reference electrode is known as, and usually it is 199 millivolt. Okay, so 199 millivolt is a standard value, because this particular electrode is a reference electrode. It is a known electrode. Okay. Then sometimes we use what is called as a calomel electrode. In the calomel electrode, the AG wire, okay, there is an AG wire or a platinum wire, and this AG or platinum wire is actually placed in a paste which is made up of mercury and mercury chloride. Okay, so instead of AgCl2, we have mercury and mercury chloride, and therefore it is called as the calomel electrode. But the problem is nowadays we are not using the calomel electrode. The reason is that mercury is a toxic metal. You know, probably you know this, that mercury is a very, very toxic element, and therefore we have stopped using this kind of an electrode, calomel electrode. Okay, and we use the normal electrode which contains silver chloride as the electrode part. Okay, this is how the electrode actually looks like. It's a photograph of the reference electrode. And can you see this point here, a whitish part here, small tube-like structure? That is the pore. Okay, which is which allows the ions to come out. Okay, or leak, you can call it. Then there is another, we have seen already the calomel electrode, and this calomel electrode generates a potential of about 2.41 volt. Okay, 2.41 volt. There is another type of an electrode which is called as antimony electrode, and here what happens is the distal end of the electrode is actually coated with a antimony ring. Okay, so there is an antimony ring. The reason here is that sometimes what happens is, if your sample is too acidic, or it is a kind of a slurry, okay, slurry kind of a sample, then usually the glass which is used for the normal electrode, that glass gets it is subject to abrasion. Okay, and because of the abrasion, the glass gets worn out very easily. The electrode gets spoiled very often. And therefore, in order to prevent that, in order to make the electrode resistant to that kind of abrasion, the electrodes are they have this antimony ring. It is a metal ring actually, which is used for the electrodes. The problem with these electrodes is that the performance of the antimony electrodes is little poor compared to the glass electrodes. Okay, then coming to the standard hydrogen electrode. Now this is the word standard is used here, indicating that this is a kind of an electrode which is used to calibrate the reference electrode. Okay, so this is a standard hydrogen electrode. Sometimes this is also used as a reference electrode, And this consists of a platinum wire in a solution of hydrochloric acid. And in this particular solution, hydrogen gas at a pressure of 1 atmosphere is bubbled, and therefore it can generate a standard potential, and this potential is actually referred to as 0 volt. Okay, 0 volt, right? And therefore this is called as a standard electrode. Okay, then I'll not read about this slide. It tells you about the properties of the electrolyte. And there is something called as a temperature sensor, which is used in a pH meter. And that is because it is a very well-known fact that if there is a difference in the temperature, for example, for every 1 degree change in the temperature, then per unit of pH change, there is an error of about 0.0035 pH units. Okay, so the meaning of the statement is like this, that if I measure a particular sample at say 25 degree temperature, and if I measure the same sample at 26 degrees, then that for that 1 degree change in the sample pH, there is an error in the pH measurement, and that error is to the tune of about 0.0035 pH units. Okay, so a sample, for example, which would normally read say 2 pH units, that sample will show you a reading of 2.0035 units if there is a change in the temperature by 1 degree. Okay, and therefore what usually is done is the pH meter itself has a temperature sensor. Okay, and that temperature sensor will automatically compensate for any change in the temperature, right? So whatever pH unit that particular meter will tell you, that instrument will tell you, that particular reading is assumed to be at 25 degrees centigrade. Okay, so even if your solution may be at 37 degree, it may be 42 degree solution. Okay, but the instrument will automatically make the correction. Okay, or automatically the error will be removed, and whatever pH unit you will see on that instrument, that is taken for granted that it is at 25 degrees. Is it okay? Here is an example here. For example, if a particular sample is showing a pH of 3 at 25 degree, okay, pH 3, then the same sample, if you take the pH at 75 degree, okay, instead of 25 degrees, then the reading that it will show is 3.67. So instead of 3, it will show you 3.67. That is an error, temperature error. Okay, so if you have a temperature sensor, the temperature sensor should also be kept in the same liquid, in the same sample of which you want to determine the pH, and there will be automatic correction for the temperature. Okay, then this is about the combination electrode. I have already told you that these are 2 electrodes combined into one. The reference electrode and the sample electrode are both combined together. Let us see how they are combined in this particular diagram. Okay, so this is the glass electrode or the sample electrode, and the reference electrode is concentrically placed around the glass electrode. Can you see this? So that is how the combined electrode would look like. And if it is not a combined electrode, then you would have to carry 2 different electrodes and place it into the sample solution. So this is a little cumbersome job, little tedious. Okay, so if you use a combination electrode, the work becomes a little simplified. Is it okay? I think the time is less. I have about 2 to 3 minutes only. So shall I continue with this? I have only 3 to 4 slides actually to show you. So I think I'll continue. And if the meeting gets over, I will again restart the meeting so that we'll complete this particular topic. Okay, and then I think most of your unit number 1 will be complete. There are 1 or 2 small topics which are remaining, and that way I think I should probably give you a home assignment so that you will be able to study yourself. Okay. So coming to the errors in the pH measurement, remember that if the meeting gets over, I'm going to restart it. Okay, so don't go anywhere else. What time is your third lecture today? Is it 1:30?
Yes.
Yes, sir.
Yes.
Okay, so at least 15-20 minutes I can give you for your lunch. Okay, so this is also a very important topic. You should know how errors are created in the measurement of pH. Okay, so two types of errors are there. Okay, one is called as the zero shift. Okay, so this happens when the electrode is faulty. Okay, when especially your reference electrode is faulty. Okay, or the pH measuring electrode, that is the glass electrode, is fouling. Fouling means what? It is already, you can say, because of some kind of decomposition or microbial, you can say, degradation taking place on the surface. Okay, or organic matter on the surface which is getting degraded. This particular electrode loses its sensitivity. Okay, so what happens in this particular case is that the potential is zero, not at pH 7, but the potential is zero at a different pH. Do you remember? Let me go to one of the earlier slides. Somewhere I have mentioned that in the standard hydrogen electrode, okay, the potential, the electric potential is exactly 000 at temperature of 25 degrees. Okay, and then all the reference electrodes are calibrated. Okay, all reference electrodes are calibrated according to the standard hydrogen electrode, and the calibration is made in such a way that at pH 7, remember this, at pH 7, the potential of these of the reference electrode is always zero. Do you understand what I'm saying? At pH value of 7, the potential of the reference electrode is exactly 0. Okay, so if you have a neutral solution, if you take distilled water, for example, then distilled water will show you pH 7, that is one thing. And if you go for measurement of the millivolt, that is the potential, then the potential will always be 0. Are you getting what I'm saying? pH 7 is equivalent to potential of 0. Just remember this. Is it okay, Amol?
Yes, sir.
Yogita Deshmukh.
Yes, sir.
Okay. What I'm saying is, always remember that for the reference electrode which is used in the pH meter, if the pH of your solution is 7, then the potential will always be 0. Okay, so that is a very clear thing. And what happens is that if there is an error in the pH meter, okay, if there is a faulty pH meter, or especially the reference electrode is not good enough, then what happens is that at a pH value of 6 or pH value of 8 or any other pH value, but not pH 7, okay, the reference electrode will show the potential of 0. Okay, or in other words, let me put it in a little different words, that if you have distilled water of pH 7, okay, then the millivolt or the potential that the electrode will show you will not be 0. It deviates from 0. Is it okay? Ideally, when you put your pH meter in distilled water, okay, then there are two modes you can do the measurement. One is the pH. Actually, you can measure the pH, and you can